I am part of a big collaboration which is called KM3net, and we are a neutrino telescope. That means we try to detect neutrinos from the atmosphere, also from the cosmos. And the neutrino is a fundamental particle. It doesn't have any charge and it has a very tiny mass, and this makes it very hard to detect this neutrino. And that means that you really need a huge detector to kind of see this particle. And therefore we have two detectors in the Mediterranean Sea. So they are really below the surface of the water. And you can imagine that we have a lot of cameras there. So when one of these neutrinos arrives, then you will see a flash of light passing through the detector, and this is what we can see. In general, we try to understand the properties of this particle better. And one funny thing that this particle does, so there are three types of neutrinos, okay? There is the electron neutrino, the muon neutrino, and the tau neutrino. And a funny thing that this neutrino does is that it interchanges between its types. So you may start here with an electron neutrino, and then as it travels, suddenly it becomes a muon neutrino. So this is what we call neutrino oscillations, and it's a property that we try to understand and to study. And in my research, I try to go even a step further than that. So I try to understand new effects in physics that could change these properties of oscillations. And yeah, one of the things that we studied recently is this neutrino decoherence. Well, decoherence is an effect that would modulate the amplitude of the neutrino oscillations, and this is something that we could then see in KM3net. I'm mostly an experimentalist. That means that I do data analysis from our neutrino telescope. My work is mostly preparing the data, understanding which kind of effects we have in the detector, and then trying to assess a sensitivity of our detector to these effects, and see if we find anything. So that's the most amazing part, when you actually see the data and you can tell, okay, what do we have here? Is this effect something that we can already see, or is it something that we cannot detect yet? The first part was to search for this decoherence effect at relatively low energies, so for atmospheric neutrinos at relatively low energies, and this part of the study is basically finished. So we have our final results. We looked at the data. We saw that we saw nothing, so to say. So we have not found decoherence, but we can give upper limits. That means we can say, okay, this effect has to be smaller than a certain quantity because we were not able to see it. And this part is already finished. Right now, I really moved to a new part where I investigate this effect at higher energies. So we will see it in a kind of a bit different way. And right now, we're running the simulations to understand how this would look like. If we actually discovered this, it would be a very huge thing, especially because, well, at the moment in physics, we still have this problem, that we have two main theories, right? We have the theory of quantum gravity on one, or on general relativity on one end, where we describe everything big in the universe, and then we have quantum mechanics on the other hand, where we describe the tiny things in the universe. And so far, nobody has managed to really have a theory of everything. And we don't really know yet what quantum gravity, for example, could look like. That would be a connection between these two worlds. But if we discovered decoherence, it would be probably a very clear signature that this could point us towards quantum gravity. And I think that's why it's also receiving so much attention at the moment, right? Because if we saw quantum gravity, it would be a first-time thing. Nobody has ever seen anything like this before, and that would be very amazing. Being published in the journal was a lot of work, mainly. We had a long review of the analysis to make sure that everything is looking good. But I also had a lot of help from other people who helped me to understand the data, to understand the statistic part. And now I'm very happy that we actually made it and that it's finally public. And yeah, I think the impact has been quite large, international also. So we have had articles about this also in other countries and also here. So I'm very happy that it received all the attention that it finally got, because it was a lot of work, definitely. So we are mostly a European collaboration, but we also have some international partners. And well, our detectors are situated in France and in Italy. So they of course have a lot of contribution. Then we have also the Netherlands, Germany and other countries involved. And especially also in my group and for my work, I had a lot of help from people with a lot of experience in this field, who, also international help, like also from theorists from other groups. So there has been a lot of collaboration with different entities within our experiment, but also from beyond that. And I'm very happy that all these people helped me.